when learning about how the discrete time Fourier transform works. You may have been confused about this line, and in fact it is a bit of a confusing line. And I specifically told you not to worry too much about what this line means because we're going to talk about it in the future. So now it's the future, and we're going to talk about what this line means, this complex sine wave, and why we need it. So first of all, you probably saw that there's something like a sine wave in this line, so it's 2 pi ft. But there's this other stuff, there's this I, or 1I, and the E, the exp. And so this is actually Euler's formula plus a sine wave, or a sine wave embedded into Euler's formula. So e to the I k, where the k in this case is the formula for a sine wave. This construction, so this is called a complex sine wave. This construction is also going to come up when we talk about Morley wavelets, which are important for time frequency decomposition. This is the MATLAB implementation of the formula for a complex Morley wavelet. And you'll see there that there's also this complex sine wave, very similar to what we have here during the Fourier transform. So what I'm going to do in this lecture is tell you a little bit about what complex numbers are, what complex sine waves are, and how we use complex numbers to extract power and phase information from the result of the Fourier transform. Okay, so this you've probably seen before. This is the square root of -1, and this is the result of this is called the complex operator, or I. So mathematicians tend to use I, engineers tend to use J because they use I for current. MATLAB accepts I or J. I tend to use I just for simplicity. So this is always a confusing concept, the square root of -1, because nothing times itself can be a negative number. Not even a negative number times itself will give you a negative number. So what does this mean? Arguably, the result of this the square root of -1 is not something that really exists in the universe. This is just kind of a construction that mathematicians came up with in order to solve problems. And it turns out that incorporating this quantity, this imaginary operator, into certain mathematics does help us solve a lot of problems in very simple and straightforward ways that would otherwise be very tedious and annoying and difficult to solve. So you don't have to worry about what it means to take the square root of -1 or what the result of this quantity actually means. You can just focus on how we use this quantity to extract power and phase information from the result of the Fourier transform, and in the future the result of complex wavelet convolution. Okay, so incorporating this imaginary operator into numbers gives us something called a complex number. A complex number is a number that has two parts or two components. It has the real part and the imaginary part. And a complex number looks something like this. So here we have the real part is 1, the imaginary part is 2i. Now when you first look at this quantity, you might be tempted to think that this is two numbers that we're adding together, and this would be a variable as if this were like x. So we would have 1 plus 2x, but actually this is not. This is just a single number, but it has two parts, the real part and the imaginary part. So here there's the plus sign here, but that's because the imaginary part is positive, otherwise this would be a -2i. In fact, all of the numbers that you are used to dealing with and thinking about your whole life are just a subset of complex numbers. So for example, the number 1 can be thought of as a complex number where the imaginary component is 0. So 1 is the same thing as 1 plus 0i. Anyway, so what's very powerful about complex numbers is that they have these two components. And if you remember from when we talked about vectors, we talked about how a vector can be, or a two-dimensional vector can just be a list of two elements, two numbers, or we can represent a vector as being a point in a two-dimensional space. And so this is the same concept with complex numbers. We can think, because complex numbers have two parts, we can plot them on, or think about complex numbers as being points on this complex plane. So this is a normal two-dimensional plane, typically you would see the x-axis and the y-axis, but now we're calling them the real axis and the imaginary axis. And so our complex number 1 to I can be represented as a point on this space. Now we can push this a little bit further, just like we did with vectors, and we can think about this point not just being as a lonely little dot here, but as being the endpoint of a vector from the origin to that point. And once we think about this as the complex number being the endpoint of a line or a vector, we can think about other quantities like the length of this line, or the magnitude. That's why I have an M here for magnitude. The length of this line and the angle of this vector relative to the positive real axis, and the projection onto the real axis, which is actually just the real component, the projection onto the imaginary axis, which is actually just the imaginary component. And you will see in this lecture that thinking about complex numbers as endpoints of a vector from the origin is a very powerful way to extract power and phase information from the Fourier coefficients. In fact, just to give you a hint into what we're going to see in the future, the length of this line is the power, and the angle here is the phase. Okay, so let's switch to MATLAB and take a look at some complex sine waves. So here we're going to define two sine waves. This is a real valued sine wave. This looks like the normal sine wave construction that you'd expect to see, sine 2 pi ft. And here we have a complex sine wave. And this is this kind of weird looking thing that you saw in the Fourier transform, e to the I k, where k is 2 pi ft. Okay, so we can plot these. First, let's look at this. So this top panel shows the real valued sine wave. Now, because we have a complex sine wave and because complex numbers have two parts, we can plot the two parts of this complex sine wave separately. We access the real part and the imaginary part using the MATLAB functions imag, so for imaginary, and real for real. So this just extracts the imaginary part of the complex sine wave and the real part of the complex sine wave. So you can see that the sine wave, the real valued sine wave, looks a lot like the imaginary part of the complex sine wave. So in fact, the imaginary part of the complex sine wave corresponds to the sine component. The real part of a complex sine wave, you can see it looks very similar, but it's phase shifted. In fact, it's phase shifted by a quarter cycle, or 90 degrees. And the real part of a complex sine wave corresponds to the cosine component. We can verify this by going back to line 10 and changing sine to cosine and plotting figure 1 again. And then now you can see that the real valued, so now this is a cosine wave, I just didn't change the title. Now you can see that this corresponds to the real part of the complex sine wave. Okay, so now here in figure 2, I'm plotting both the real part of the complex sine wave and the imaginary part of the complex sine wave on top of each other on the same plot. So you can see that they're very similar. Not surprisingly, they have exactly the same frequency, but they are phase shifted from each other. Okay, so now we're just looking at the projection of this complex sine wave onto this two-dimensional space, where this is time and this is amplitude. We can now view these in slightly different ways. So this is what a complex sine wave really looks like. It has it's a three-dimensional being. It has extension in time, extension on the imaginary plane, and extension on the real plane. So now you can see that this sine wave looks like a slinky. It's sort of spiraling through time. And now if we were to rotate this axis to project through the imaginary axis, and just, oops, that's not what I wanted to do. This is what I wanted to do. Through the imaginary axis, so now we just see time and the real part. Now you can see this is the familiar looking cosine, and we can do this the other way and project through the real axis, and now we see the time axis and the imaginary axis, and now you see this looks like the sine component. So in fact, when you look at a plot like this, or plots like this, really these are just projections onto two axes of a three-dimensional function. So we can also project through time, and now we see the imaginary part and the real part, and you can see this just looks like a circle. Later on in the future, when we do complex Morley wavelet convolution, you will see that this distance does not always change. If you make this plot, you'll see that things are spiraling around and they get closer to the center and further away from the center. But here with this constant amplitude sine wave, the amplitude is always 1. The distance from the origin of this space is always 1. And so time is just cycling around over and over like this on top of itself. And that's how we get this plot figure 4. You can see I'm plotting the imaginary part by the real part. And this comment in line 49 is just to show you that if you plot a complex sine wave like this, or a complex number like this, MATLAB interprets this line 49 and line 48 in the same way. All right, so that's kind of neat. But now when we go back and think about the Fourier transform, this changes slightly our interpretation of what's really happening in the Fourier transform. So now in the Fourier transform, at each step of the Fourier transform, we have the data, and now we are computing the dot product not just with a regular sine wave, but with a complex sine wave. And when we do that, this means that the dot product is going to have two components, so it's going to be a complex dot product. The dot product will have a real component and an imaginary component that corresponds to the cosine wave and the sine wave. Okay, so now when we compute the dot product at each frequency during the Fourier transform, and before I was showing you that each dot product can be represented just as a bar, but this is not entirely accurate, or that bar is a further step. What we really get, the raw result of the Fourier transform, what we call the Fourier coefficients, these are actually complex numbers. These are complex dot products. And so what's happening inside each of these bars, really at each frequency, is so this would be the result of the dot product between the complex sine wave at this frequency and the data. And now you can see that this is going to change at each frequency. Okay, so now let's try and think about what this result means and what we do with this result. Okay, we have to take a brief aside to talk about rectangular notation and polar notation. So here, this is very similar to what I showed earlier. We can think about complex numbers. This is from a book called DSP Guide, which you can get, I think it's dspguide.com or something. You can find it somewhere. So this is an engineering book, so they use J, but you know that this is the same thing that I've been calling I. So here's a complex number, and we can represent this on this rectangular plane using this notation. So we have 2 over on the real axis and 6 up on the imaginary axis. Turns out we can also use something called polar notation to represent this same point, this same quantity. So here we can say that 2, 6j is the same thing as m is the square root of 40, and theta is the arctangent of 6 over 2. So I encourage you to pause the video now and think for a minute about how we got these numbers from this and what these numbers might mean. Okay, so probably you had to reach far back in your brain and call to mind all these trigonometry classes that you took when you were in middle school or high school. And maybe you had the insight that this point, we can think about a right triangle as this point, and then this would be the hypotenuse going from the origin to that point. And then we can drop a line, project down to the real axis, and draw a right triangle here, or right angle here, so this is a right triangle. And now we can apply the Pythagorean theorem. We can say that the length of this line is the square root of a squared plus b squared, or 2 squared plus, so 2 squared is 4, 6 squared is 36, And so it gives us the square root of that gives us 40, and then the length of this line is the square root of that. So this is a squared plus b squared equals c squared. Furthermore, the angle of this line, so that tells us how far this point is away from the positive real axis, that we can get using trigonometry. So the tangent of this angle is equal to the ratio of the projection onto the imaginary axis over the projection of onto the real axis. So theta equals arctangent 6/2, which is the imaginary part over the real part. Okay, so I hope this is sensible. Maybe it's trivial, or maybe it's a little bit weird to think about, in which case you might want to go back and review some basic trigonometry. But the important thing here, what's powerful about this, is that we can translate between rectangular notation and polar notation fairly easily. So we can describe this same point using a number of different methods. So yeah, this is just reviewing what we saw in the previous slide. We can translate from rectangular to polar notation, and from polar notation to rectangular notation. This means that we can describe this point in complex space using a plus ib, or we can describe this point using more sort of trigonometric notations of the cosine component plus the sine component, and the m here refers to the distance away from the line. Now this becomes very interesting because of something that this guy taught us. So this is a picture, I presume, of Euler. Now Euler was he was a Swiss mathematician, so he was Schweizerdeutsch. And so if you would ask a German-speaking person how to pronounce his name, they would say something like Euler. There are two reasons why I tend to prefer pronouncing his name as Euler rather than Euler. Partly because I think that's how I first heard people talk about this guy. So I have this sort of primacy imprinting effect. But also in English, if you say the word Euler, many people would think of something like this. This is, an oiling can that you would use to put oil into an engine. That's something. Anyway, you can call him Euler or Euler, it doesn't matter. This is his famous formula. E to the I k, I'll just call this k for now. E to the I k equals cosine k plus I sine k. So this part looks familiar from the previous slide. And now what Euler showed is that we can equivalently represent this information as e to the I k. Just as a further aside, Euler is known for many formulas, and if you study graph theory or linear algebra, you will learn about Euler's formula, which has nothing to do with this equality. In the context of time frequency analyses and extracting information from complex numbers and oscillations and things, this is really the only Euler's formula that is really relevant. So I will say, for the rest of these lectures, I will say things like Euler's formula, I'll refer to Euler's formula. I'm really only referring to this, but of course Euler was a very prolific mathematician, and he is known for more formulae than just this thing. Anyway, this means raising a complex number that's this to the natural log base, that's the e, gives a vector with the length of 1, an absolute value of 1, and an angle corresponding to the real component of that number. I'll show you what this means in the next slide, but basically the point is that this quantity is a very efficient way to represent oscillatory information using polar notation that allows us to extract power and phase information from the results of a Fourier transform or from complex Morley wavelet convolution. Okay, so here's what Euler's formula looks like graphed out. So here we have this complex plane. Again, this is the real axis and the imaginary axis. And here we have a polar plane that's superimposed on top of this. So now we see this vector, and this point here would correspond to the result of a complex, computing a complex dot product at each step of the Fourier transform. And so what we have here is we can represent this point and this vector either as cosine k plus I sine k, or we can represent this using e to the ik. Now here, this is a unit circle and this is a unit vector. So we don't need any, so there is no amplitude information or magnitude information here. If this vector were shorter than 1 or greater than 1, then we would have an m out here, so m would be the length of this line. And then we'd have m e to the ik equals m cosine k plus I sine k. Okay, and so this is really how we extract power and phase information from the Fourier coefficients from the results of the Fourier transform. Here we have a sine wave in the time domain, and when we compute the Fourier transform at the coefficient corresponding to this frequency, we would get a number like this, a complex number. This is the dot product between the complex sine wave at 3 Hertz and this our signal, which happens to be a sine wave at 3 Hertz. And the result of complex, the complex dot product is this point in this space. And now we take the amplitude, which I'm plotting here. The amplitude is the magnitude of this line. And the phase, which I'm not plotting here, but will become relevant in the future. The phase is the angle of this vector relative to the positive real axis. And so this is why we need these complex numbers. I'll get back to this point and I'll review this information and talk more about it in the lecture about extracting power and phase information from complex Morley wavelet convolution. But the basic idea is that if we didn't have these complex numbers, all we would get is the projection onto the real axis, which is not very useful, certainly not very useful for well, it's impossible to get power and phase information out of this if we only had real sine waves. Okay, so let's take a look at this in MATLAB now. Now we can go down to the cell that starts on line 53. And here what we're going to do is create 3 sine waves. I should say cosine waves. The amplitude of these sine waves is 3 to 1, and the phase is going to vary here. Then what we're going to do is compute the Fourier transform of these, and then we're going to extract just the Fourier coefficients at 6 Hertz. So I chose 6 Hertz here because these are 6 Hertz cosine waves. So let's see. So if we look down here at the Fourier coefficients for the first sine wave, the second sine wave, the third sine wave, then so here's the real part and the imaginary part of the Fourier coefficients. And it's kind of hard to map any of these numbers back to either the amplitude or the phase information. So if we look at this, the real part here, so if you would multiply this by 2, that would basically be this amplitude, but it's not easy to see how we would get the phase information. And for the other 2 sine waves, it's even less clear. So 0.85 times 2 is not 2, and 0.5 is not pi over 6. Anyway, the point is that it's not possible to reconstruct the amplitude and the phase information just from looking at the Fourier coefficients. What we need to do is combine the projection onto the real axis and the projection onto the imaginary axis in order to extract power. So how do we go about doing this? Well, if we go back here, I told you that the length of this line we take as the amplitude. And so to extract this, we need to take, we need to compute the magnitude of this line, which we can compute as the square root of the real part squared plus the imaginary part squared. And to take this, we can take the arctangent of the imaginary component over the real component. Okay, so that's what we're going to do here. In fact, we're going to use, in this example, we will use the MATLAB functions ABS, which extracts the magnitude of a complex number, and we're going to use the angle, MATLAB function angle, which extracts the angle. Later on, you'll see we'll do this manually. All right, so here in this polar plane, I'm plotting the Fourier coefficients at 6 Hertz from these 3 sine waves. So now you can see that this lines up nicely. So here, the red line is for sine 1. It has a magnitude of 3, or an amplitude of 3, which corresponds nicely to this, and has an angle of 0, which corresponds to the angle that we specified, and so on for these other guys. So sine 3 has an amplitude of 1, that's what we specified, and an angle of 60 degrees, which corresponds to pi over 3 radians. Okay. So now we can unpack this a little bit further. Here I'm going to compute the amplitudes of the Fourier coefficients. And here I do it the sort of manual way using the Pythagorean theorem. So we take the square root of, well, this I guess b squared plus a squared, and then the square root of that is the amplitude. Now you can see this is our Fourier, or the Fourier magnitude of the Fourier coefficients for these 3 lines, and of course these 3 sine waves, and of course this maps on very well to what we specified up here in the code. And this here, the commented lines on lines 94 through 96, this just shows you that doing it the manual way through the Pythagorean theorem is the same as the MATLAB function ABS. So in practice, I always use the MATLAB function ABS. It's certainly easier than writing out all of this code. And now for the phase, we see the same thing. We can take the arctangent of the imaginary component over the real component, and this gives us the phase angles. Now you might initially think that you should use the function a tan and then do the imaginary divided by the real component. You can do this, but of course when the real component is 0, then you're going to be dividing by 0. So that's a difficult problem to deal with. So the function a tan 2 deals with situations like this where the real component would be 0. And this is just to show you that the MATLAB function angle produces the same result. In fact, I believe the function angle is really just computing a tan 2. Oh yeah, okay. So it's no shocking news that this function produces the same as this function. So in practice, I recommend using the function angle. Okay, and I think that was it. Let's see. So that's it. I hope you found this informative. The point of this lecture was really just to show you how to deal with these complex numbers in the Fourier transform. This issue is going to come up over and over and over again. It's a very important issue. So if anything was confusing, then you can go back and review the literature, review this lecture. I'm also going to review this material again when we do the complex Morley wavelet convolution videos.